Welcome back to linear algebra. In this video, we're going to be evaluating determinants. The idea of a determinant is one that has a very interesting history in the study of equations. It actually predates the description of algebra as anything other than solving polynomial equations. The things you learn in high school and college algebra, we now call the theory of equations as just one branch of algebra. Linear algebra is something different, and there are other algebras that you may study in the future. In any linear algebra class that you will ever encounter, the ideas of determinants are always tied to matrices. A matrix is a really nice way of condensedly describing what a determinant is trying to do. Historically, the determinant showed up in very unrelated ways. The determinant was used as a tool for solving systems of equations before matrices were formed. Depending on the algebra courses that you took prior to this one, you may have come across what's known as Cramer's rule, which was developed well before matrix notation was ever introduced. If you've taken several semesters of calculus, you may have come across the Jacobian matrix, which is a way of describing relative changes in functions of several variables. The determinant definition there, again, predates the matrix entirely. For our purposes, we're going to build up the determinant as a way of determining when a matrix is invertible, right? That laundry list of equivalencies that we had not too long ago, the fundamental theorem of inverse matrices. There's going to be one more tool added to the list involving the determinant. We'll get to there in a future video. And once we get there, we'll be able to use the determinant as a very powerful tool for solving the eigenvalue problem. But for right now, I just want to look at the determinant as a tool of computation. All right, let me get my head out of the way, and let's start at the beginning. The determinant of a matrix is a function which maps a square matrix to a real number. We're going to denote the determinant using the abbreviation DET, similar to how you've seen, right, sine, arcsecant, logarithm, abbreviated using a couple of letters. Determinant is DET. It maps from square matrices. The set of matrices in general is written using a script M with a subscript on the rows and columns. So in general, we're going to say from n by n matrices into the real numbers. Let's make that look like an R and not a D. There we go. When we write the determinant, there's a couple of different notations it can take. Right? If I have, let's start with a 2 by 2 matrix. A equals components A, B, C, and D. If I want to talk about the determinant of matrix A, and I want to give it by name, determinant of A is very common. It's not very common, but every now and then you'll come across the absolute value of A as a notation here. And again, it's not absolute value. This is the determinant of A. Right? That one's not very common, but it does exist, and I did want to mention it. And it exists like that because it actually is very common to take your matrix and instead of using parentheses or square brackets to define your matrix, to use vertical bars that look like absolute value bars. All right, so matrix A, B, C, D with vertical bars instead of square brackets means the determinant of the matrix instead of just the representation of the matrix. That can get very confusing for a 1-by-1 matrix. Because the determinant of matrix A, well, we denote it with vertical bars and we write the arrangement of the matrix inside, and it looks like it says absolute value of A, but it doesn't. It says the determinant of A, and you get out the value of A. The determinant of the matrix -7 is -7. Right? Again, determinant of a matrix is not absolute value. We do not care about absolute value in linear algebra. It's not a function that shows up. We use this notation that looks like it says absolute value for something that is not absolute value at all. And when you get to the 2-by-2 case, it becomes pretty straightforward and everything works fine. All right. The definition of the determinant of a 2-by-2 matrix, I always think of as diagonals. Take the main diagonal, take the off diagonal, and subtract them. AD minus BC. All right, that is the definition of the determinant of a 2-by-2 matrix. So if I have a particular 2-by-2 matrix here, like 1, 3, -5, 4, taking the determinant here is going to be main diagonal 1 times 4 minus off diagonal 3 times -5. In this case, I get 19. One more example just to highlight, even though we use things that look like absolute value bars, this is not absolute value. You can get negative numbers when you take a determinant. -2, 5, 7, -3. All right, -2 times -3 minus 5 times 7 is 6 minus 35, which is -29. Taking the determinant of a 2-by-2 matrix is fairly straightforward. When it comes to taking the determinant of a larger matrix, we use a process known as cofactor expansion. You may have seen cofactor expansion as a tool for dealing with the determinant of a 3-by-3 matrix. If you have, that's fantastic. It absolutely works. 3-by-3 matrices are pretty common, and specifically the determinant of a 3-by-3 matrix is pretty common in a number of applications you may have come across in previous courses. Right? The vector cross product being a key example, and those things that I listed at the beginning of this video, Cramer's rule, the Jacobian, and so on. But you may have seen a different process for a 3-by-3 matrix. There's a couple of neat tricks that work for the 3-by-3 case that do not extend further. So if you've seen a different way of taking the determinant of a 3-by-3 matrix in the past, I really want you to take the time to learn this method instead, because it will extend into other larger matrices without any issue. All right. So to do cofactor expansion, let's start with a matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. A very interesting matrix. Easy to remember. Easy to make sure you know what's going where because everything is different. The rules of cofactor expansion are that you choose a row or column and you expand on it. If you've learned this in the process of the vector cross product, you learned specifically to expand across the top row, which is perfectly valid. All right, you do have to know where you are starting. We're going to call this the 0 position. 1, 2. And so we want to count to wherever we're starting. In this case, we don't have to start very far at all. 0. When you are starting at an even position, this is a little bit easier. When you're starting at an odd position, you're going to end up with your signs, positive and negative, backwards. I'll show you what I mean with another example on this matrix in just a moment. All right, but I'm going to take the first entry where I'm expanding, which is a 1. And then I'm going to multiply it by a 2 by 2 matrix. I am going to eliminate the row that I'm expanding on, and I'm going to eliminate the column that gave me the first entry that I wrote down, the 1. When I do that, it leaves behind a 2 by 2 matrix. In this case, it is the matrix 5, 6, 8, 9. And so I will multiply 1 times the determinant of that 2 by 2 matrix. Then I subtract. You're always going to alternate between adding and subtracting. The second entry in the row I'm expanding on is a 2. And if I eliminate the row and column containing the 2, it leaves behind the 2 by 2 matrix 4, 6, 7, 9. Then add, and the last entry in this row was a 3. And when I eliminate the row and column that contains the 3, it leaves behind 4, 5, 7, 8. The method of cofactor expansion turns taking the determinant of an n by n matrix into taking the determinant of n slightly smaller matrices. In this case, I went from 1 3 by 3 matrix down to 3 2 by 2 matrices. And I know how to take the determinant of a 2 by 2 matrix. 5 times 9 is 45. 8 times 6 is 48. 4 times 9 is 36. 7 times 6 is 42. 4 times 8 is 32. 7 times 5 is 35. 45 minus 48 is negative 3. 36 minus 42 is negative 6. And 32 minus 35 is negative 3. So I've got negative 3 plus 12 minus 9, which in this case is 0. All right. So expanding across the top row is the usual way of dealing with cofactor expansion, but you can in fact expand on any row or column that you would like. Let's take a look at the same matrix again. 1, 2, 3, 4, 5, 6, 7, 8, 9. This time, I'm going to expand down the second column. Starting here at my first entry, if I count over, I have to move one place to get to this -2. So from 0 to 1, right? 1 is odd. So instead of being a positive starting value, I have a negative starting value this time. Again, just count over. You can think about starting at 0 and counting. That's how most books set it up. You can also think about just alternating positive, negative, positive, negative. So if we start here positive, this is negative, positive, and negative. All right. It works out the same way. You get the same result, but we said that was going to be negative. It is the 2 here. We eliminate the row and column that contain that 2, and we're left with the matrix 4, 6, 7, 9. Alternating, we will now add. The next entry in the column we're expanding on is the 5. We eliminate the row and column that contain the 5, and it leaves us with the 2 by 2 matrix 1, 3, 7, 9. And then alternating, after adding, this time we will subtract. We've got an 8 there, and eliminating the row and the column, we're left with the 2 by 2 matrix 1, 3, 4, 6. All right, 4 times 9 is 36. 7 times 6 is 42. 1 times 9 is 9. 7 times 3 is 21. 1 times 6 is 6. 4 times 3 is 12. So we've got -2 times -6 plus 5 times -12 minus 8 times -6. So that's going to be 12 minus 60 plus 48. And yes, we get the same 0 that we got in the last example. All right. So why does it matter? For a lot of people, myself included, when I was first learning linear algebra, it didn't become obvious. Why can we care that we can expand on any row or column? Why don't we just pick the first row and just always expand on the first row? And then some point further down the line, I was presented with a problem that really would have been easier if I had thought about it ahead of time. That is, what happens if instead of an arbitrary matrix, you have a triangular matrix? So let's take a look at this matrix. 4, 3, 7, 9, 2, 0, 1, 8, 5, 6, 0, 0, 9, 0, 3, 0, 0, 0, 4, 8, and 0, 0, 0, 0, -1. This is a 5 by 5 matrix. I would much prefer to find ways of making my life easier as I go through this. And it turns out that there's a really nice way to do so because I have all of these zeros. If I can find the row or column with the most zeros and expand on that, it's going to make my life a lot easier. And in this problem, I have that immediately. Watch what happens when I expand down that first column. I get 4 times the result of eliminating the row and column which contain the 4, which is this 4 by 4 matrix. It's a bit of a mess, but 1, 8, 5, 6, 0, 9, 0, 3, 0, 0, 4, 8, 0, 0, 0, negative 1. Then continuing on, alternating positive and negative. So for the next one I subtract, I've got a 0. I'm going to multiply that 0 times the determinant of a 4 by 4 matrix. But who cares what it is? Because whenever I figure it out, I'm immediately going to multiply by 0. And multiplying by 0 makes the whole thing 0. And then the third entry, plus 0 times something. The fourth entry, minus 0 times something. The fifth entry, plus 0 times something. I don't need to know what any of those cofactor matrices are, because when I take the determinant, I'm going to get a number, and whatever number it is, I'm going to multiply by 0, and I'm immediately going to get 0. So by finding that column that was mostly zeros, I was able to shortcut literally 80% of the problem. And it gets better, because now I need to handle the 4 by 4 matrix. And the first column there has a bunch of zeros. All right, so eliminate the row and column that have the 1, and we're left with this 3 by 3 matrix, 9, 0, 3, 0, 4, 8, 0, 0, negative 1. All right, let's put some serifs on this 1 so it doesn't look like a vertical bar. Then, continuing down, I get 0 times some matrix plus 0 times some matrix minus 0 times the determinant of some other matrix. And by choosing the correct place to go with all these zeros, I shortcutted 75% of the second step. Cleaning up a little bit, this is 4 times the determinant of that 3 by 3 matrix. And we can keep doing this. Go down that first column again, and we will have 4 times 9 times the determinant of a 2 by 2 matrix, 4, 8, 0, negative 1, plus 0 times the determinant of a 2 by 2 matrix. I'm sorry, that should have been a minus. Right? Alternating signs, plus, minus, plus 0 times the determinant of another 2 by 2 matrix. And again, I don't care what those 2 by 2 matrices are, because I'm going to multiply them times 0 after I take the determinant, and whatever number I got out, it just turned into a 0. So I just saved myself 67% of this step. All I have to do is 36 times the determinant of the 2 by 2 matrix 4, 8, 0, negative 1. All right, so 36 times negative 4 which is negative 144. All right, use zeros to your advantage. If you can find a row or column that has a bunch of zeros, find a way to get there and expand on that row or column and save yourself a lot of effort, especially as the matrices get bigger. All right, let's end with a problem like this for you to try. I'd like you to define the determinant of this 6 by 6 matrix. Yeah, that's a lot of zeros in that matrix. That's what makes this a reasonable problem for me to give you. But I've got 0, 3, 8, 0, 4, 0, 0, 0, 7, 0, 1, 0, 2, 0, 0, 0, 8, 0, 3, 0, 0, 0, 0, 0, 0, 5, 0, 8, 0, 8, 0, 0, 4, 1, 0, 0. All right. I would like you to take a couple of minutes and use the method of cofactor expansion to find the determinant of this 6 by 6 matrix. All right, see what you can do with that, and I'll see you in the next video.